mega science projects is helping greatly in the development of new products, services and new ideas. One such product is the creation of world's biggest ground-based optical and infrared telescope of 30-meter diameter aperture. It is a result of the quest for understanding fundamental issues like the possible existence of life beyond the solar system, the dark energy, believed to be causing expansion of the universe to accelerate, and many other astrophysical phenomena like formation of planetary systems and formation and evolution of stars and galaxies. TMT would enable Indian astronomers to study front-ranking scientific problems such as formation and evolution of stars, planets and galaxies. India has collaborated with the US, China, Canada and Japan to build the TMT at an estimated cost of about 1.47 billion US dollars. With this, India is set to contribute in making its very crucial components for the telescope. In fact, many crucial parts of the telescope are already being fabricated at various institutes across the country. Under the joint responsibility of Department of Science and Technology and Department of Atomic Energy, the Indian science sector will benefit both scientifically and technologically. It will bring in the know-how for new and cutting-edge technologies and will make possible gathering information about early stages of evolution of the universe.
The telescope is a 30-meter diameter, and 30-meter diameter is not one single meter. You cannot make a single meter of 30 meter. Casting itself is difficult, and then putting there and then moving around the sky is much more difficult because it sags, one single meter. And also to transporting, you cannot make a 30-meter transporting. So this is now built as a segments. So it has a 492 segments. Each segment is 1.45 meter diameter. And these are going to be aligned, and then they had to make them all act as a single mirror. To make them act as a single mirror, and then you need to have sensors. They sense during the night when you are chasing the stars across the sky. The telescope has to move from one position to another position. So during that time, things happen. Okay, the gravity changes where they are. Some mirror will be somewhere else, 30 meter away. Another mirror is here, and then because of the temperature changes, the height changes. So there is going to be a change in the position of the mirrors, relative positions, from one mirror to another mirror. So each mirror is going to be attached some 6 sensors. What these sensors do is they sense the relative displacement of these segments. Okay, whether they are how much the displacement is. So that entire sensor thing is India's part.
You can collect more light from these objects, celestial objects, and basically, suppose if you want to see the object which we cannot detect with a smaller telescope, so this can be seen with the help of 30-meter aperture. So the sensitivity of the telescope, which increases with the diameter, and the image sharpness increases when the aperture increases. So these two together, the sensitivity of the telescope increases a lot.
So once this displacement information is gathered by the sensor, then sent to the actuators, and then the actuators, what they do, they nudge these mirrors. There is some displacement from, nudge that mirror goes slightly up or down, something like that. So the entire actuators we are making in India. So those are some 1,600 actuators we are to make.
It is also set to give finer details of not so far away objects like undiscovered planets and other objects in the solar system and planets around other stars. 30-meter telescope being the largest optical and infrared telescope in the northern hemisphere will enable several discoveries which will surely inspire future generations. The project will also provide state-of-the-art high-end technologies to the country. which would benefit a number of industries and research and development centers of India.
The monolithic mirror, the maximum size, the conventional telescope which is available across the globe is 8-meter class. So the difficulty in making bigger than 8-meter class is making the mirror. So monolithic mirror, anything bigger than 8 meter is difficult. One is that the fabrication facility, and another one is that handling the mirror, supporting the mirror, because when you go for the bigger mirror, so its weight increases, which needs a totally a complex supporting system, and its thermal inertia increases, and various other problems come into the telescope. And the mirrors are going to be fabricated in our optics facility. The facility is coming up in one of our campus. It's called Crest campus of IIA. So the segments are going to be produced there in that facility using a special technique. It's called stress mirror polishing technique, and we are going to put the machineries and the required accessories and the metrology tools in the facility for making the stress mirror polished mirrors.
The design of the project has just been completed and is in its early construction phase and is expected to be operational in early 2020s in Mauna Kea on the island of Hawaii. While India is collaborating with the international scientific fraternity to conquer space, it has always been in the forefront of developing indigenous optical telescopes. Vainubappu telescope with a 2.34-meter diameter mirror at Kavalur Observatory in Tamil Nadu was commissioned in early 80s. It could easily resolve a 25 paise coin kept 40 kilometers away. Deep sky observations could be carried out with this telescope. The world-class 3.6-meter Devisthal optical telescope, another feat achieved in this field, was remotely activated jointly by the Prime Minister of India and the Prime Minister of Belgium in 2016. Located at Devasthal near Nainital, it is the largest steerable imaging telescope in Asia, which is a result of scientific collaboration between the team of scientists from Aryabhatta Research Institute of Observational Sciences, Nainital, also known as ARIES, an autonomous institution of DST, and the Belgian scientists.
In 1980, when I joined this observatory, there were plans to have larger telescope, but it was realized that the larger telescope cannot be put here because of expected light pollution. So site survey to find out some good site was carried out in Uttarakhand area, and after long experiments, long observations, the Devasthal site was found suitable for a larger telescope. Now where we have a 3.6-meter telescope.
Located at higher altitude in the central Himalayas and away from big cities, Devasthal is best suited for carrying out observations in background condition and to study the regional environment, particularly interactions between the natural and anthropogenic trace species and climate change. The telescope will contribute to the observations for frontline scientific research in astronomy and astrophysics. It features an optical spectrograph, a CCD imager, and a near-infrared spectrograph.
With regard to Devasthal, the prevailing wind throughout the year is from southwest, and in about 5-kilometer radius of this site, there is no peak higher than this peak, and hence there is no wind sink. So due to this laminar airflow at Devasthal site, we are getting, we measured and we got the seeing of 1 arc second. That is the kind of median seeing we got. And since we have established the telescope that is about 10 meter above the ground level, so the effect of free air seeing is reduced further. So in fact, we are able to see the effect of seeing only to the level of 0.3 to 0.4 arc second, not more than that. So as a result, this telescope is capable of giving you images of sub-arc second.
The telescope is also the first of its kind in India that features an active optic system, which compensates for small distortions in the shape of 4.3-ton mirror due to gravity or atmospheric aberrations. The polarization measurements help understand the nature of some of the stellar and extragalactic sources. Light from astronomical objects is in general polarized to some degree, and its measurement gives additional information related to the magnetic field, the distribution of scattering material, and the non-thermal nature of light.
If the light will be polarized in a particular angle, the intensity will be increased. The polarized light comes to you. The source is there. Source is not an instrument. Instrument has just to find it out whether the light coming from the star is a polarized or not. So if the light coming from the particular object or a star is a polarized, then you are able to see what is the source of the polarization in there. If the source of the polarization is, for example, say scattering or say the reflection, so you are able to see that what kind of the sources are there. If it is a scattering, that means some material is in front of that particular star, which is scattered and giving the polarized light. That is light vibration along the one direction. Okay, so if you have this, then you are able to study that particular object in more detail.
To achieve a good signal-to-noise ratio, the 3.6-meter Devasthal optical telescope also uses polarizing filter.